Hello everybody, and welcome to another Linux assembly tutorial. Let's just get the slideshow started. What is that thing? It doesn't matter. Okay, today we're going to go through just a few general things about what exactly assembly language is, and then I want to finish up with, hold on a second. Okay. That's good. That's really professional. Nice. We're going to talk about a few general things about assembly, and then we're going to finish up with an example of AT&T syntax, the same example as we programmed last time in Intel syntax. Alrighty, so first of all, what is a CPU? Assembly programmers are primarily concerned with a particular piece of hardware called the CPU, which is short for Central Processing Unit. And the CPU is really the brains of the computer. It controls all of the other devices. It does a lot of calculations and a lot of divvying out of the tasks to other devices. So your CPU tells your graphics card when to do graphics. It tells your sound card when to make sounds. And yeah, it pretty much just runs the whole show. You've probably seen it on the motherboard. They're usually in the top left-hand corner of the motherboard. And they've got big fans sticking out of them. Anyway, you probably know that already. So the CPU understands only numbers, and it reads and writes numbers in groups of 8 or more binary digits, and binary digits are called bits, incidentally. Even the instructions for what the CPU is meant to do are encoded in numbers. Yeah, these things are number crazy, really. They don't understand a single piece of text or anything. Every single thing they do is nothing but billions and billions of numbers. Above this right here is the machine code for multiply 3 by 5. So the instructions are encoded in numbers, and these are the instructions or the machine code to multiply 3 by 5 to an x86 CPU. Each different CPU manufacturer will have their own machine code, but this is x86 CPUs. So almost everything nowadays, desktop computers use x86. It's only mobile devices and other things like that that use different ARM-based CPUs. Who cares? Okay, so machine code. Assembly programmers occasionally use machine code. Yeah, we'll go into how to program direct machine code, I hope, at some point in this tutorial series. It's not usually useful, but sometimes it is useful to go into real machine code. And one of the perks of using assembly is that you're so close to the hardware that you are able literally to just program in machine code and then dip in and out of machine code and assembly anytime you like. Anyway, hopefully we'll go through that in a future tute. So this particular bunch of bytes just here, the machine code from the previous slide, I would translate to something like B8 means move the following immediate value into EAX, and we'll look at EAX in a lot more detail later. The 0, 3, and all of the zeros after that, so that's these numbers just here. I hope you can see my cursor. They're actually a little endian D word. How cute, little endian D word. We'll look at exactly what that means later as well. The following line, 6B, means something like multiply, and C0 means EAX is the source and the destination for the multiplication, and the 5 is the number to multiply by. So my point here is that machine code is really confusing and very, very difficult. Machine code's extremely confusing, and thankfully there is an easier way. Yeah, there is indeed. We can program assembly, and we can type something like this: mov EAX 3 imul EAX EAX 5. This is assembly language right here, or ASM for short. It's the language of the CPU, the machine code that we just saw, only instead of numbers, we use easy to remember symbols called mnemonics. For instance, mov is short for move. That's pretty easy to remember. You put an E on the end and you've got move. Imul is short for multiply. And there's also actually a mul instruction, but we'll look at all this later. But imul is signed multiply. Anyway, EAX is a register, and 3 and 5 speak for themselves. So you can probably see that this is a whole lot easier to read and write as coders than the pure machine code from the previous slide. But the important thing to know is that assembly and machine code aren't really different languages. They're basically the same thing with the words swapped around a bit. So assembly's instructions map directly to x86 machine code. Yeah, this line, MOV EAX3, means exactly that previous slide's machine code. They're the same thing. Okay, a lot of people started asking, why learn assembly? After I uploaded the last shoot, and I just want to go through a few pointers here. Yeah, I think if you're here watching this tutorial video series, you probably already have a few reasons for why you'd learn assembly, but these are a few of my reasons. Number one, I think probably the most important reason is to understand the CPU. So the CPU itself is just an amazingly powerful piece of hardware, and it's absolutely incredible that so many clever people around the world have come together and since the 1970s created this ridiculously powerful piece of hardware. And assembly language is actually etched onto the silicon. It's part of the CPU. The CPU and its assembly language aren't two different things. In a sense, a CPU is its assembly language, give or take a few more things. There's registers and that sort of stuff. But in another sense, an assembly language is its CPU. They're both the same thing, sort of. Yeah, you can't really split them up. So that's really important. If you understand an assembly language, then you understand the hardware itself. Alrighty, point number 2. There's things we can't do with high-level languages. Yeah, there's a whole bunch of things that you can do in assembly, or that you can ask a CPU to do in assembly, that you can't ask it to do with high-level languages. And hopefully we'll go through a few of those. Some of them are pretty interesting. They don't come up a lot. C++ or C, they're really powerful languages, but some things are just impossible, or very difficult to do with C or C++. And they're very simple to do with assembly. Number 3, here we go. It's fast. Do you know what? I'd probably use a superlative here. It's not fast, it's the fastest. It's the fastest language you could possibly program a CPU in, because it's its native language. So often an algorithm programmed in pure assembly will perform much faster than the same algorithm programmed in something like C++. Not always, however. Not always. Yeah, it's very easy to write a really slow algorithm in assembly as well. Anyway, we'll go through all that. Okay, number 4, to understand how a high-level language works. Yeah, if you look at the way that C++ works from the point of view of assembly, you get a really different view of what's happening. What C++ appears to be doing and what it's actually doing are two very different things. And it's really interesting to see the way that C++ works. And I think you become a better programmer all round in high-level languages when you learn assembly language. Okay, number 5, and this is debatable, number 5, but I believe that assembly is a far simpler language than high-level languages. Yeah, you look at something like the new C++, C++11, and don't get me wrong, I mean, I love the language, and I'm always very excited when a new C++ comes out, but I tell you what, it's complicated. C++ is amazingly complicated. It's one of the most complicated and useful inventions of, all time. And assembly, despite what you might have heard, is actually really simple. Yeah, it's nothing but reading values and setting values, one line after another. Really simple. Anyway, number 6, it's a different language. Yeah, what does that mean? It's a different language. You tend to acquire problem-solving skills that you wouldn't normally acquire if you stick to your C-based languages. Yeah, you might have learned a whole bunch of languages in the past. Say you've learned maybe BASIC and C and C++. You've learned Java and C#. You mightn't be surprised to hear that they're all pretty much the same language. You probably noticed that they're all, basically just different accents of exactly the same language. They're all C-based languages in the end. Even Python. I mean, give or take a few curly brackets here and there, and all of a sudden you get something very C-based when you look at the way that Python works. There's also HTML-based languages, which are quite different from C-based, but there's a whole family of HTML-based languages. If you learn one, you almost know them all. Assembly is nothing like either of these families. it's its own family of languages. And like I said, each CPU has its own assembly language, and they're very, very different. You'll acquire different problem-solving skills, which is really, really important as a programmer, I feel. Since programming is nothing but problem-solving. Yeah, one problem after another. Another language also, incidentally, I mean, if you want to really open up your eyes and see something that's just very, very strange, you might try looking at Lisp. L-I-S-P. The Lisp language is just bizarre. It's completely different from all of these languages as well, so that's a real eye-opener. Yeah, give Lisp a look if you like. Very, very cool. Okay, Intel versus AT&T. Yeah, I think I might have disappointed a few viewers with my last shoot because I stuck to Intel syntax, but in the future shoots we're going to go through both Intel and AT&T syntax. So the remainder of this shoot will actually code the same example as last shoot, only instead of using Intel syntax with ASM, I'm going to use AT&T syntax with GAS. Thank you very much to the viewer also that pointed out that you can actually change GAS to use Intel syntax. Yeah, that's very, very useful. So thank you for that information. Anyway, in the future we'll explain them both. Okay, that's good. So let's get to coding. We're going to do the same thing as we did last time, only this time we'll use AT&T syntax and the GAS assembler. Once again, I'm going to use C++ because for most things, there's no need to code entire applications in assembly. It's just slow. I mean, if you're doing sort of your own operating systems and things like that, there's no other choice. But most of the time, you'll use some other language to do the high-level stuff. So I use C++. Anyway, I've got a blank directory here, a blank folder. So what I might do is start by making the C++ file, cpp. Okay, include iostream. How many times have I typed this? Okay, using namespace std int get value from gas. Okay, so that'll be the function that we code in native assembly. Oops. Pretty basic front end here. We're just going to call that function and print out whatever it returns. Gas said gas. You just can't type gas everywhere. That's not programming. There's a lot of things that aren't programming. You look at sort of sausages or balloons, or even like the Leaning Tower of Pisa, or the Eiffel Tower is another one. Yeah, that's not programming. You can't just type gas. Okay, let's not talk about what's not programming. I think what we're here to do is talk about what is programming, so let's just get back on track. Get value from gas. End all. Okay, so that's my C++ front end. All we're going to do is call a native assembly function called get value from gas, and then we're going to exit. So if I just hit Control O to save that and Control X to get out of there, now we'll make the assembly file. So nano asm.asm. I'm using nano as well. I mean, this is a tiny program. There's no reason to use something that can deal with a gigantic project when we're just doing this very basic stuff. So section.text. The gas assembler calls them sections instead of segments, and it calls it the text section instead of the code segment. Okay, that's good. Get value from gas. Okay, so we want to sort of export or make available, make global a label in this file so that when the linker comes along, it can figure out that this get value from gas label is actually available to the C++ that we just wrote. Okay, get value from gas. Okay, that's the label just there. Mobile, dollar, we'll say 25, and %EAX. Alrighty, so that's your AT&T syntax assembly right there. So Movel is move long, or move 32-bit. 25 is the value that we're moving, and EAX is where we're moving it to. We'll go through exactly how you actually pass values between these things a bit later, but for now, we'll just make that nice, simple little program. Okay, so that function should be callable now from that main, so long as we link them both together. The first thing that we've got to do is create an object file from asm.asm. We compile it to an object file using the gas assembler, which is the AS command in the terminal. So asm.asm, that's the source code file, and output asm.o. There we go, so that should have made, yeah, it did, right there. So I'm pointing to it, but you you probably can't see it. I don't think the screen recorder records what I'm pointing to, unless I do it with the cursor. Yeah, there we go. Okay, very clever, good. Okay, so the next thing that we've got to do is compile main.cpp with the G++ compiler, the GNU C++ compiler, and link that to asm.o. You'll remember that in main.cpp it requested that we call a particular function, and it's not defined in main.cpp, it's defined in asm.asm. So we've got to link it. Anyway, asm.o and main.cpp and o, and I'll say run me. Okay, so what we want to do is compile main.cpp, we want to link it to asm.o, and the output file that I want to make is runme. And there it is, runme. Okay, so let's give it a run. And there we go, so gas said 25. Good program. Very, very useful. So if you want to know what gas said, it's 25. Okay, so a few other things that we might want to do. We might want to check if runme is a 64-bit executable. This tutorial series is not about 32-bit x86, we're talking about x64 x86. So what you would do, or one way to do this, is file runme. And there we see runme, elf 64-bit. So it's definitely a 64-bit executable, which is exactly what we want, since we're using our modern CPUs for what they're best at. The file command just here just gives you a bit of information about the file. So that's pretty good. What we might also want to do is instead of using EAX, we might want to use RAX, the 64-bit register, since we're in 64-bit assembly. Okay, so what you can do to change this and use RAX instead of EAX, I mean there's no real point at the moment, but you change that to Q, mov Q, and then RAX. Output and X to save, and as asm.asm, output asm.o, and G++, asm.o, main.cpp, and out runme. Okay, so you can use the 64-bit register as well if you want, but it's not going to make a difference here, since in main.cpp we said that get value from gas returns a 32-bit integer, so C++ is actually only reading EAX, it's not reading RAX. Anyway, that's not really relevant, we'll go through all of that stuff more in the future. Okay, so that's a little example of how you might code the same example as last time in AT&T syntax using the gas assembler. Hopefully in future tutes I'll go through the syntax to both of these assemblers, NASM and gas, since I think they're both really good. I mean, I like the way AT&T works. Some of the things it does really, really well. I think that the AT&T syntax is closer to the machine code. If that makes sense. I mean, assembly's really close to the machine code no matter what syntax you use, but I think AT&T syntax is even closer. Okay, so a little introduction to assembly there. Thanks for listening. See you later.